The next speaker is Vsevolod Afanasev from Novosibirsk State University, Sobolev Institute of Mathematics, and I think Mathematical Center in Akademgorodok. So, Vsevolod, please, your time.
Thanks. And not there's not just my affiliations, of course, but for the other author as well. So yeah, thanks a lot for the opportunity to be able to participate in that workshop. And this talk is based on my joint work with Andrei Mamontov on the not so graph-related topic as was already mentioned, but it is quite algebraic nonetheless. And it will be quite substantially overlapping with the talk I was given during the Maltsev meetings in November, but it was in Russian, so that's that. So we will be considering the following class of groups, which are named n-transposition groups. Simply put, a group is an n-transposition group if it is generated by a set, which we denote D, that consists of involutions or elements of order 2. Secondly, it needs to be normal, that is, it should be closed under conjugation by the whole group G. And last but not least, definitely, the order of the product of any two elements of D doesn't exceed n. So from here, the n in n-transposition comes up. While the transpositions, well, mainly because the initial and the motivating example was the permutation groups for, I think, n greater than 3. So all the symmetric groups are the free transposition groups, and the D in this case is the set of all transpositions. It's quite a well-known fact that the symmetric groups are generated by transpositions. So this explains the namesake. Other examples are the alternating groups, which are 6 transposition groups, and with the set D being the set of products of 2 cycles, so products of transpositions, if you will. Additionally, there are multiple examples of free transposition groups among some other groups, like the symplectic groups, the special unitary groups, and the orthogonal groups. And the interesting examples here also from the finite group theoretic point of view, so to say, are the sporadic groups, namely the Fisher groups, which are free transposition groups, and also the 2 largest sporadic simple groups, the baby monster group and the monster group, which I have denoted by blackboard B and blackboard M. And there also is a whole Janko group, or the second Janko group, which is a 5 transposition group, and it kind of was added to this list specifically for the purposes of this talk, because it cannot be constructed as an subgroup of index 2 in the automorphism group of a certain interesting graph. Additionally, we have a possibly infinite example of an n-transposition group. More specifically, it is an extension of the Burnside group of exponent 5, that is a 2-generated group of exponent 5, which is extended by a cyclic group of order 2. Currently, it is unknown whether the B25 group whether it's finite or not, so this is a possible example of the infinite transposition group. Hence, we do not mean our groups to be finite, but they will almost always be finite during our talk at the very least. So what do we know about these groups? We know quite a lot about the free transposition groups. Namely, all of them are, all the centerless groups, of course, are classified for all the centralist free transposition groups are classified. This was started by Fisher, who in his paper in 1969, he used some additional restrictions, but he was able to obtain quite a rich number of examples. And in particular, he was using the so-called the 2 invariant graph structures on the set D, which I introduced earlier. Namely, he was using the so-called commuting graph, which I'm not really, I'm just throwing this out there because it's not really important to the topic of the talk, but it probably isn't somewhat in the spirit of this workshop. Perhaps, maybe not. So as I was saying, Fisher used the so-called commuting graph where the vertices correspond to the elements of the set D, and they are connected by the edge if and only if these elements of D commute, which is equivalent to their product having order 2. And this job was, this classification was finished by Gorges and Hall in the 1990. And additionally, they showed that any finitely generated free transposition group is finite. And coming to the more recent results, in the year of 2022, Hall also provided an explicit number of generators for all finite free transposition groups. I don't know why I worded it that way, but I did. For when we move to other values of n for other n transposition groups, we do not have as many results. In fact, all of the classification results are pretty partial and are reduced to some finitely generated examples. So here's a bit of notational convention. We say that a group is M generated if it is generated by M elements from the set D. So the set D may include a lot of elements, but if only M suffice, then we say that the group is M generated. So as it is said on the slide, the following subcases for greater values of n are classified. In particular, Pasrov, McInroy, and Spektorov classified all three generated finite four transposition groups. And Mamontov, Sarletov, and Wybrow classified all minimal free generated 6 transposition groups, with minimal being a rather restrictive property, which I will not elaborate upon for now. And additionally, the closest work to the ones we've been doing is the work of Dessel, who classified all free generated finite 6 transposition groups, where 2 of these 3 aforementioned generators commute, and they also satisfy the so-called 2A condition, which I will elaborate upon further down the line. I'll kind of summarize, if I may. As was said, the results for free transposition groups are quite rich. There is a serious theory of which led to the classification, while for bigger values of n, like 4, 6, and even 5, there are the results are somewhat scarce. So what we are doing is we are considering free generated 6 transposition groups, as again with 2 of the generators commuting. So in other words, we study the 6 transposition homomorphic images of the group given by the following presentation. And to be a bit more graphical, no pun intended, we present this picture. So at the edges of the triangle, there are the generators, the involutions X, Y, and Z, and the weights of the vertices, if I may so say, mean the order of their product. So X and Y, the product of X and Y has order 2, so they commute, and the other orders are R1 and R2, which run from 1 to 6 due to the 6 transposition property. And we do not require the 2A condition, which means that the product of X and Y needs to lie in the set D, because this restricts the situation quite a lot. And it is natural, if we wish to classify the groups which satisfy these properties, it is natural to consider various values for R1 and R2, and this is exactly what we were doing. So let me get to the main result. If we say that R1 and R2 are both not equal to 6, then we have the following list of, I'll say that more clearly. So then all 3 generated 6 transposition groups with a commuting pair of generators are finite, and they are either solvable or they are homomorphic images of one of the following groups which are listed here. For convenience, I'll recall that the double dot means the extension the split extension to be precise, which can also be viewed as a semi-direct product. And the dot here means just a non-split extension, or in this case, it's a triple cover of the S6, and in this case, it's a double cover of the group, of the mature group on 22 points. And we also know the solvable groups explicitly, but for brevity, they were omitted from this table. And we have made some progress for the case of R1 and R2 equal to 6, but the result is not finalized, so we do not present it here. I'll now move on to some ideas which we use during the classification. And in many cases, it is possible to use the strategy of trying to find some groups that quote unquote look like free transposition groups, because we know that the theory of free transposition groups is quite rich and we have a lot of results regarding them. So it's quite natural to try to reduce the case of classifying the 6 transposition groups to free transposition groups. And one such subgroup is a normal closure of one of our generators, which we denoted X. It so happens that this normal closure is either 5 or 6 generated, and this whether it's 5 or 6 generated depends on the value of product of Y and Z, and it looks like a free transposition group, meaning that it has a Coxeter diagram, which looks like a Coxeter diagram of free transposition group. In this case, I'll explain the graphs. So, at the vertices, we again have the generators, the involutions, elements of order 2, and we have a vertex between. Oh wait, we have an edge between 2 vertices if the product of the corresponding involutions has order 3, and we do not have an edge if the corresponding involutions commute. So for example, for this particular case where R1 is equal 4 and R2 is equal to 5, we have that X commutes with X to the power conjugated by product of Z and Y, but the product of X and X conjugated by the product of Z and Y squared has order 3. And you can read the other diagrams in a similar fashion. And this is the case because all these products are similar to the squares of these products. And since all of these 3 products are products of elements from D, which normally might have values, the orders might range from 1 to 6, but their squares range from 2 in the set 2, 3, or 5. So whenever they take values 2 and 3, it is quite simple to reduce this case to a free transposition group case. And we do it using the relations from the paper by Hall and Soicher, or Zoicher, I don't really recall how to say his name, unfortunately, which classified all 5 generated free transposition groups and provided specific presentations. And basically, we check the corresponding relations in the groups which we obtain, and we look for the situations whenever this normal closure is indeed a free transposition group, which allows us to quite easily obtain the isomorphism type of the whole 6 transposition group. But this approach does have a few problems. In particular, the number of relations that we need checking grows quite quickly when we iterate through values of R1 and R2. And secondly, when one of the aforementioned orders, I'll jump to the previous slide, one of these orders has a value equal to 5, the idea basically does not work. So we use some auxiliary ideas in these cases. I'll present one of them. So if we are given a subgroup generated by involutions such that all product orders are odd and they do not all equal to 3, then we can use the properties of dihedral groups to obtain a non-trivial centralizer element for any involution which generates that subgroup. So for example, if we have the following case where the product of X and R1, where R1 is equal to 6 and R2 is equal to 5. I may have misnumbered them, but that doesn't really change the picture. We can take the following element, we can conjugate Z by X to obtain the group with the corresponding diagram. Then we can use the properties of the dihedral subgroups generated by Y and Z conjugated by X and the remaining one, in order to obtain a non-trivial centralizer element for Y. And this allows us to obtain some meaningful relations which we can exploit in order to classify our groups even further. And these and similar ideas, they almost entirely free us from using computer calculations, because we are able to use some effective reductions and well, but at many situations we did require computer calculations, in particular when we were working with some sporadic groups as the Matthew groups. We had no choice but to use the coset enumeration algorithms provided by the gap computing system, for example, in order to determine what group we have actually obtained. So this is it. Thank you for your attention. And if you have any questions, I'd be glad to answer them.
Yeah, thank you so much for your interesting talk. So are there any questions, comments? So maybe I have some easy questions. Maybe I missed some details, but do you assume that in the main theorem that your group is finite, or it follows from something easy, or you prove this?
Yeah, we actually prove that, because we, for the values which we specified, we run over the classification. Well, I mean, yeah, they are always finite. We prove that because if we place the relations that should, the constraints on the some product orders that need to be satisfied in a 6 transposition group, and we always end up with a finite group. So yeah, we prove that.
Yeah, I understand. Perfect. And the classification of such solvable groups follows from something, yes?
No, it does not. We just, as I said, I just left them from this table for brevity's sake. The techniques we applied are precisely similar to the groups listed in the table.
Yeah, I understand. And as I understand, maybe I'm not right, this topic is somehow related to Majorana algebras, yes?
Absolutely. It is very closely related to the Majorana algebras and to the axial algebras that generalize the topic, because the automorphism group for some specific for some type of axial algebras, which includes Majorana algebras. So if you have such an algebra, then its automorphism group is always a 6 transposition group. So if we classify those, we are getting closer to the classification of automorphism groups for Majorana algebras at the very least.
No, I understand. And I think the main goal of this work is to use this result further for Majorana algebras in some sense, yes?
Yes, but not necessarily. For instance, one can one can use this as a stepping stone to classifying all other 6 transposition groups, at the very least pre-generated, because you can always obtain such a configuration from there, almost always. Yeah.
I understand. Yeah, it's very interesting, and at least for me, it's a new topic. So thank you